Section 8.8, surface tension. First, let me ask you a question. If you have 1 milliliter of water, okay, or any amount of water, without gravity, what's the shape of the water? Well, you'll say spherical. And why is that? So let's talk about the theory. For a reversible process at a constant temperature and volume condition, if there is non-expansion work, this dA is equal to du minus Ts. All right, du is dq reversible plus dw reversible. And then we can do further derivation here. dq reversible is Tds. We copy this dw reversible here. If the temperature is constant, dTs is Tds, and then we have dA is equal to dw reversible. And work can be expansion work, that's PDV, non-expansion work here. If the volume is constant, the work, expansion work, is 0 because this dW expansion is negative PDV, that's 0. So dA is just dW non-expansion. The change of the Helmholtz free energy is simply the non-expansion work. And if we look at the non-expansion work of a liquid droplet, well, it's gamma times d sigma, where gamma is the surface tension and sigma is the surface area. We'll get back to this gamma a bit later. Now, I'm going to ask you this question again. If you have, let's say, 1 milliliter of water, it prefers to adopt a spherical shape. But you can have 1 drop of water and you can divide this water into 1,000 droplets, right? Which one is preferred thermodynamically, favored thermodynamically? Which one has the lower A, the lower Helmholtz energy? 1 drop or 1,000 smaller drops? Well, the answer is 1 drop, because when you have 1 drop, you have smaller surface area. How much smaller? Actually, if you divide 1 drop into 1,000 drops, the radius is going to be only 1/10 of the initial radius. Therefore, the surface area of the smaller droplet is only 1% of the larger liquid droplet. But you have 1,000 such droplets, so 1,000 times 1%. That means by breaking 1 drop into 1,000 drops, you increase the surface area 10-fold. That's bad. But then why is that bad? Why a large surface area is unfavored? Well, it's very simple. On the surface of a liquid, such as water, the molecules can only form half of the hydrogen bonding. So if you have water inside the liquid, it can form hydrogen bonding with all surrounding water molecules. But if you put it on the surface, it can only form hydrogen bonding with roughly half of the water molecules. There are just no water molecules on this side. There are water molecules on the inside, not outside. That's the reason you want to maximize the number of hydrogen bonds. So that's the reason. So to reduce this A has to be minimized under the constant temperature and volume condition. You need to reduce the surface. And also you can just easily see this gamma, the so-called surface tension, can be calculated by the change of this A divided by the change of the surface area. So surface tension can also be used to explain this 2 phenomena. Capillary one is this capillary elevation, one is capillary depression. So this is capillary elevation or capillary rise. I think this is just water inside. This capillary tube is made of glass, I believe. The glass is made of sodium silicate, I believe. Because of the strong attraction between glass and water, so water is joining up, okay, to increase the area, the contact area between water and glass. Again, this is because the attraction between glass and water is greater than the attraction between water and water. This, I think, is mercury. This is still the same glass capillary. The attraction between the glass and mercury is smaller than the attraction between mercury and mercury. And therefore, this mercury is trying to minimize the contact area, between itself and the glass. There's also a way to compute the surface tension experimentally. So let's say we have a capillary tube, and then we form this meniscus, and then we have this pressure difference, this rho GH. This is caused by the surface tension, so we have this equation. This is the equation for the pressure change caused by the surface tension. This is the pressure change, and therefore surface tension is just rho GHR over 2 cosine theta. And you can see this is the R, and this angle is the theta, and this H is simply the elevated liquid.